Hey, welcome back. We are deep in the investigation of the convergence or divergence of these infinite series. We recently just saw the integral test, which is super useful in determining whether an infinite series converges or diverges. Though you may have been thinking this as you were seeing the explanation of the integral test, that's only really going to work when the expression inside of our infinite series is easy to integrate. And if you've had experience with integration, you know that's often not the case. In this video, what we're going to introduce are two comparison tests. What these will allow us to do is, given certain conditions, is look at the convergence or divergence of a more simple series, often something like a p-series. And if we can determine the convergence and certain conditions are met, we can make a statement about the infinite series we are investigating. All right then, right to it. Here is our first comparison test. Here we're comparing two series, one described by the a sub k's and one described by the b sub k's. Important here in this case is that in each of these series, the terms must all be positive. That's really important. As you will see, we'll soon talk about alternating series where we have negative and positive terms. We'll have to do some finagling to use a test like this. But in this case, we're only considering series with positive terms. Also to say, in this video, I'm being a little bit lazy about my notation, but this is pretty dang standard at this point. I'm not going to write my iterative variable where it starts and write infinity. I'm just saying, you know, both of these are infinite series. Where our variable starts does not really matter in each of these cases. This will hold true in either case as long as both of these series are infinite series. So first up, we know if the a sub k's are less than the b sub k's for all k values, and we know that the b sub k series converges, then we can state that the infinite series created by the a sub k's also converges. So in the same way, if we know that for all k, the a sub k's are greater than the b sub k's, and then the b sub k diverges, then we also know that the series created by the a sub k's also diverges. My hope is that both these two statements are a bit intuitive to you and they make sense, especially since we're restricting to positive terms, which means the sequence of these partial sums must be monotonic. And so if we look at this state right here, that we have the infinite series created by the b sub k, if that converges, so if the sequence of the partial sums converges, and we have the fact that it's basically bounding the sequence or the series created by the a sub k's, it makes sense that if that b sub k series converges, then the a sub k converges also. In the same way, if we have this divergent series created by the b sub k's, but these a sub k series, each of these terms are a little bit greater, well, if you have this divergence of this one series, and this is bounded below, so it's above the other sequence, again, thinking of the sequence of the partial sums, then it would make sense that it diverges. But let's take a second, and at least for the first statement right here, I'll give a somewhat rigorous proof of why this works. All right, so in order to prove this conditional statement, what we're going to do is assume the if part and see if we can show that it implies this convergence of this series right here. So we're assuming that the b sub k infinite series converges, and we're assuming that we have this fact that for all k, the a sub k's are less than the b sub k's right here, and also just stating that they're all positive terms that will help out. So if we now make a statement about the partial sums of this a sub k infinite series, so we know that this the s sub n can be written like this. So we'll start from k equals 1. Again, where we start doesn't actually matter, but let's just make this look a little bit more formal. So we know that this is the equivalent to this statement right here. But because of this nature right here, we know that that must be less than or equal to the nth partial sum of the b sub k sequence. So nothing too radical right there, but importantly, we also know that this nth partial sum must be less than or equal to the actual convergence value of this infinite series created by the b sub k. And we also know that this converges, which converges to an actual value we'll call L. I also want to note real fast that this is important to state right here, is that this is only true that this infinite sum is going to be greater than the nth partial sum for the b sub k's because we're dealing with only partial terms. So every time you have a term, we have these positive terms that increase steadily. And what that statement is telling us is that for all n values, so all of these partial sums, the s sub n's, or the partial sums, are less than or equal to L, which directly implies that the sequence of these s sub n values is bounded. So we know the sequence of these partial sums is bounded, but since all a sub k's are greater than equal to 0, we also know that this sequence of these partial sums is monotonic. Therefore, by the beautiful bounded monotonic theorem, this partial sum sequence converges, which implies that the infinite sum of the a sub k's is convergent. And I won't spend time proving the second statement right there, but it can be proven in a very similar way. But let's do an example of using this comparison test and see why it's useful. In our first example here, we're being asked to determine whether this series converges or diverges. And it's the series starting at 2, the infinite series starting at 2, of the natural log of k over k cubed. You'll find as we go through this and using the comparison test, it's really useful to have some sort of intuition of whether it converges or diverges. You'll see in my statements with my limit comparison test, it's not always necessary that you know that. You can take guesses outside of it, but it can make your life a lot easier. But importantly here, I digress and I'll come back to that thought in a second. What I want to do is compare this to an easy series to determine convergence or divergence. And what I'm noticing is that this natural log of k is actually less than k. So I'm going to use a p series to compare this. So I know that the natural log of k is less than k, and this is true for all k greater than 0. Obviously, if k is less than 0, this is undefined, but we don't need to worry about this because k is this iteration variable. That's these positive whole numbers. But if this is true, I can divide just both sides of this inequality by k cubed. I know that the natural log of k divided by k cubed is strictly less than k over k cubed. But importantly, k over k cubed can be reduced down to 1 over k squared. So what I have in that statement, importantly, is that these terms right here, we'll call these the a sub k's. These are strictly less than these terms, which I'm going to use as my b sub k's. And looking at this right here, specifically, if I look at the infinite series created, and I'll just use the same indice here of 1 over k squared, I know that this is a p series with p equal to 2, thus it converges. So what I have here are the two statements that I need. So I have this relation between these terms, that these natural log of k over k cubed are strictly less than 1 over k squared. I also know that this sequence, because it's a p series, or this series, excuse me, is a p series, I know it converges with p equal to 2. So then, by the comparison test, I know that this sequence, that k starts at 2 to infinity, of the natural log of k over k cubed converges. Just to go back to a statement I made a couple minutes ago while working on this example, this is only a useful inequality if I know or expect this to be a convergent series, right? So if I'm going to use this comparison test, if I have this fact where I have these a sub k's that I'm looking at right here as my sequence, and they're less than a b sub k, that's only useful if the series made of those b sub k's converges. And that if it doesn't converge, then it doesn't make, I can't use this at all and it makes no statement. And in the other way, if I'm going to look at b sub k's that are less than my a sub k's, it's only useful when using the comparison test if that series made of the b sub k's diverges. And I just want to continue that thought for 1 second. What we were just working with, we used the fact that the natural log of k over k cubed is less than 1 over k squared. And that was useful because we had this convergence, we had this sandwiching of sorts where this is bigger than this, and we can use the comparison test. But the question is, in this case that I want to tackle, and we'll use our new limit comparison test, what about something like the natural log of k over k squared? Right out the gates, you might be thinking like, well, that's not a big deal. I can just compare that to 1 over k in exactly the same nature I just did. Well, it is true that the natural log of k over k squared is strictly less than 1 over k. But really importantly to this statement is I have this inequality that I need, but this 1 over k as a p-series I know is divergent. But it's also true that this statement right here is greater than 1 over k squared, and this, as a p-series, is convergent. And I bring this up just to emphasize this idea about the inequalities, is that, well, if I think this is convergent, what I'm going to look to is to find a convergent series whose terms are greater than or equal to the series I'm looking at. If it's divergent, I want it to be greater. But this right here, this natural log k over k squared, doesn't satisfy both of these, at least for these obvious p-series that I'm looking at. And an example like that should give us the drive to find another comparison test. So we can compare these p-series, but maybe in a bit more rigorous way. And here we have the limit comparison test, which shouldn't be a surprise, is using a limit in this comparison that we had for the first comparison test. We have exactly the same setup. We have two series that are infinite series and have positive terms. And what we're looking at here is as we take the limit, as k goes to infinity, we're looking at the limit of the ratio of these k terms right here. And we have three cases. So in the first case, if the limit of this ratio is equal to L, so some constant that's not 0. It's important that it's not 0 because 0 is our second statement right here. What we know then about these two series is that they're harmonious in their convergence and divergence. So if the limit of this ratio as k's go to infinity is a constant, then we know both the infinite series of the a sub k's and the infinite series of the b sub k's either both converge or both diverge. So if we knew something about the convergence of the b sub k, we could make a statement about the series of the a sub k's. Number two, what we have here is that if that same limit goes to 0, so there's something here when you're looking at this, is that as k's go to infinity, these b sub k's are growing fast enough that makes this limit go to 0. This is a bit of a rational function of sorts, right? So if we have that nature and we know the b sub k's converge, or that's the series based on the b sub k's converges, then we know the a sub k infinite series converges also. And finally, C is kind of the opposite of B right here. If we take the limit of this ratio right here and it goes to infinity, and we know that the series of the b sub k's diverges, then we have a statement that the a sub k's diverge also. Whenever you're using these comparison tests, especially as you see it set up right here, we think of the b sub k series, as we had in the first comparison test, as our standard series. We know something, or it's easy to compute something about that series, and it's going to give us an implication about the a sub k series as long as we satisfy all the conditions. As with the first comparison test, I'm not going to prove all of these cases right here. They're all very similar. In this case, I'm going to choose to pick case B right here. So what I'm going to do is assume this part of this statement. So I'm assuming the if part, that we have this limit, it goes to 0, and the b sub k converges. And we also know about some relationships between limit statements and sequences. In this case right here, I know that if this statement is true right here, the limit of these equals 0, then I know that the sequence that is made up of these terms right here, so as we increase k, I know because the limit is equal to 0, this sequence is bounded. But what that means right here, if this sequence is bounded, what it means is that there exists some m value for all k. Again, if you're not used to these, again, these are just statements. This means there exists an m for all k such that the a sub k's over b sub k's are less than or equal to m. So there's nothing crazy there. All I'm stating is what this means right here to be bounded. What it means, there's some value, some constant that's always greater than the ratio of these terms right here, which are the terms of this sequence. But if this is true right here, I can multiply over these b sub k's. What I know that's true for all k values, the fact that the a sub k's are less than m times the bk. Well, this is extremely important. By the way, you might be looking at this. This is part of, I'm going to use our first comparison test to make this proof right here. But I have this inequality statement. But it's also true that if this converges, so since I know that this series converges, by the constant multiple rule, I know that also this series converges. Well, then we have it. What I have is that we're now comparing the a sub k series with not b sub k, but this m times b sub k. That I know there exists this m. I know that if this converges, this must also converge. So then by these two statements, so by 1 and 2, and the comparison test, it must be true that the sequence of the a sub k's converges. All right, and I won't leave you hanging. Let's now tackle the convergence of this natural log of k over k squared. We established this interesting relationship in the inequalities of 1 over k squared and 1 over k. Again, the issue was with the comparison test, we need this expression, these terms that we're looking at, to be less than a convergent series or greater than a divergent series. And we're kind of in this kind of purgatory between these two. But the question is actually, can we now use the limit comparison test to attack this? And I also want, in this example, to kind of model, if you're a student and getting used to this, how do you play around with this? And here's what I would do right away. Given this statement right here, what I'm going to do is compare these terms that I'm looking at to both of these terms to see if I can use any one of these cases. So here I have two different limit statements. In this first limit statement, I'm comparing the terms of this series with 1 over k squared. And the second example, I'm looking at 1 over k. And I'm doing this to model the fact that you can do this. If you're rigorous in your effort, you can quickly find these limits to kind of get an idea. It's not really much work, as I hopefully will show you right here. So again, I'm not making any decision about these convergence or divergence. I know about those. I'm just looking at these limits, comparing these two right here. So this expression right here is exactly the same as the limit as k approaches infinity of, so this is going to flip up, the k squareds cancel, this just becomes a natural log of k. So as k goes to infinity, this function right here goes to infinity also. Okay, so we'll check on that in 1 second. That would be something like the third case right here. Limit of k, as k goes to infinity of this statement right here, I would flip this, cancel, I only cancel one of those k's, so what I get is the limit as k goes to infinity of the natural log of k over k. I actually feel like I know this limit, but let's just be a little bit rigorous about it. I'm going to apply L'Hopital's rule, because as k goes to infinity, the numerator and the denominator both bloat up to unbounded to infinity. So I'm going to apply L'Hopital's rule here, and this will give me that the limit as k goes to infinity. Well, what does L'Hopital's rule does? On the denominator here, this is just going to turn into a 1. The derivative of the natural log is 1 over k. Without showing all those steps, I'm sure it's easy to verify. This will become 1 over k, and as k goes to infinity, this becomes 0. All right, so we've evaluated these two limits pretty quickly. In this case right here, I have this limit going to infinity, so we can test this real fast. So we have the limit between these two goes to infinity, and the question is, does the summation of the b sub k's here diverge? And unfortunately, it's a p series, p equals 2. This actually converges, and so the limit comparison test fails in that case. But no worries, let's try b here. We have the same limit with these a sub k's being, the b sub k's being 1 over k. We get that the limit is equal to 0, so in this case right here. So if that b sub k converges, actually it doesn't. The 1 over k we know as a p series diverges. And so I didn't do these examples to waste your time, but just to show you the process through which you need to attack these. It's often not that you're going to just know the answer right away. I mean, as you grow in your knowledge, you'll have a better intuitive sense about what to do. But I thought this was just a fine attack. I look at these limits, hoping these would work out in the way that I want, but they were switched around. Am I completely at a loss? Or can I think of maybe a p-series between these two? And yeah, what I'm going to do is attack this, but I'm going to let the p-value, so this exponent right here, be right directly between the 1 and the 2. I'm going to let it be 1.5 or 3/2. And so as I just said right here, if I look at this series right here, 1 over k to the 3/2, this is a p-series where p is 3 over 2, larger than 1, so I know that this converges. I mean, for me, it's hard to think about, can I make a statement? It's an inequality statement, but actually I don't need to at all. That inequality statement was simply for the original comparison test. For the limit comparison test, all I gotta do is compare the limit. So what I'm going to do right now is look at the limit as k goes to infinity of the series that I'm looking at. So these terms are natural log of k over k squared divided by this series that I want to compare it with, which is k to the 1 over k to the 3/2. And then in simplifying this statement, again, I'm just going to flip this over and multiply. I'm going to get a k to the 3/2 over k squared. When I reduce those factors of k, what I'm going to get is the limit as k goes to infinity of the natural log of k. I'm going to have just k to the 1/2 down here in the denominator. And now I will apply L'Hopital's rule again, and I'll show this out a little more explicitly. And that gives me taking the derivative of the numerator and the denominator, since I know these go to infinity, is 1 over k over the derivative of this would be 1/2 k to the negative 1/2. Then let's clean this up a little bit right here. So we have the limit as k goes to infinity. What I'm going to do is move this up into the numerator right here and flip this 1/2. So I get 2 times, so if I have k to the 1/2 over k, what I actually will get is k to the 1/2 or the square root of k here in the denominator. And actually now as k goes to infinity of this limit statement right here, it goes to 0. So then I have it right there. I have the limit of the natural log of k over k squared divided by the 1 over k to the 3/2. I found that that limit goes to 0. I also know that that p-series right here converges. Thus, I know that this series right here converges. So there we have two very useful new tests. And again, what we use those tests for is if we're looking at some expressions, we're like, man, the integral test would be great, but that's a gnarly looking function. What we can do is compare the terms of the infinite series that we're looking at with an easier to determine series. Often a p-series will be your baseline or a series that you've recently worked with. And in this case right here, to me, it's a bit trippy and it's pretty awesome, is that this is somewhere in this world between acting like 1 over k squared and 1 over k. 1 over k, the harmonic diverges. This 1 over k squared p-series of p equals 2 converges. The question was, like, where on this continuum is it closer to? And this isn't mathematically rigorous, but I would say my feeling about this is that this term is closer to 1 over k squared than it is to 1 over k because it does converge.